Good morning. I shall carry on Porter-Governor discussion. I shall continue it. Professor Pavan has introduced you the topic governor. You already know what is governor. Governor is an attachment to a prime mover which will help to run the prime mover at a constant speed. Why constant speed, etc. I shall keep it, and if necessary, I shall come back and probably in your notes also you come to know why it is required. So we all have understood the requirement of the Porter governor in general, and we have two types of governors: certificate governor and inertia governor. There are again certificate governors are very common because they are very easy to construct, but inertia governors are not that easy to construct, therefore they are not that common. So in centrifugal governors there are a variety of types depending upon the construction, but as per our syllabus we are supposed to discuss the two types of governors. One is called as Porter governor, the other one is called as Hartmann governor. Okay, Hartmann, both of them are called as loaded governors. And what is the meaning of loaded governor and what is unloaded governor? Probably I shall take it up maybe in your notes, through notes, or I shall explain it sometime later. So now I would like to take up the discussion of Porter governor. So any centrifugal governor, we all know that essentially every centrifugal governor shall have a spindle, so a sleeve and a skeleton, and which will carry what is called as governor balls. So I have drawn only half of the Porter governor here. Okay, this is the Porter governor, only half of it I have drawn because only half of it I will be considering for the analysis purpose, and you have exactly the symmetric thing what you have on this side. So this line indicates the governor spindle. I have represented it by only axis. The complete spindle has not been shown, and even the arms. The upper arm, this is the AB is upper arm and BC is lower arm, and this portion is what is sleeve. Okay, so this is the construction of a Porter governor which I have shown. Okay, please observe it carefully here. Okay, this is the axis, and imagine that this is the collar at the upper end, and this collar is not going to move at all, either up or down. Okay, it is not going to slide, it is fixed. And similarly, I have a sleeve. This is a sleeve, and this sleeve will go up and down depending upon the speed of the governor balls. And this is what we call it as say A, B, C. And similarly, the other side also we have this side, and the upper arms and lower arms and the collar, all that together is what is called as the skeleton. And this is what is called as governor ball 1 I have shown, and a similar thing you have on the other side. Okay, so please see here some of the construction, whatever is required for the analysis, that also has been shown here. Okay, the governor means this is the fixed part which is fixed to the spindle, and the upper arm, this is the lower arm, this is the sleeve, and this is the ball. Okay, so now let me assume that the governor, okay, the spindle is rotating. The governor spindle is rotating as the upper arm, this collar is fixed to the spindle. The whole skeleton also will be revolving. So let me assume that the governor spindle is rotating at a constant speed. Constant speed. And why it is running at constant speed? Because this governor spindle, which is connected to the shaft of the prime mover, and the prime mover is running under a constant load, and therefore the speed of the prime mover is constant, and hence the speed of this also, the governor spindle, is also constant. And this governor balls are revolving at a constant radius. Say this is r in the radius of rotation. It is rotating at a constant angular velocity. And I know that since these balls are not moving either outwards or inwards because of the constant speed, and hence I can say that these balls are revolving at a constant radius, and now I can say that with respect to the horizontal movement, say in this plane, these balls are in an equilibrium state, and therefore I can easily apply what are called as equilibrium conditions. That's what I am going to do in this analysis. So before I really go to that, I have two terms. So these terms are going to be useful and for solving the problems later on. And the analysis, whatever I carry on, is not with any purpose of deriving any expression or any equation. My aim of showing is how to analyze any Porter-Governor problem. That is my purpose. Therefore, though sometimes I may use the final expression here, I wish to treat this method of analysis for solving every numerical problem which we will be taking it up later on. Okay, so before I proceed, I have few terms. One is called as RCU, radius of collar at the upper end. Okay, this distance, the upper arm is hinged away from the axis. So this distance I got as RCU, and I am showing the analysis with RCU some distance. But sometimes in some numerical problems RCU may be 0. So in that case, this point A is also on the axis of the spindle. So similarly, I have what is called as RCL. This is the radius of the collar at the lower end. This also may be 0 in some numerical problems. LU, length of the upper arm, LL, length of the lower arm. So I have assumed LU and LL of different lengths. So I would like to make this analysis as general as possible, which will cover all the cases. But in many problems, the length of the upper arm may be same as length of the lower arm. In that case, LU is equal to LL. And R is nothing but the radius of rotation of the balls. So this is the axis, this is ball, and this is the plane of rotation of the balls. These balls are revolving like this in this plane, and this is what I can call it as horizontal plane of rotation of the balls. And the distance between the axis and the center of the ball is what is called as the radius of rotation of the ball. And omega is the speed at which these balls are revolving, and this is in radians per second. And all these distances are in meters to have consistency later on. Though they may be given in millimeters, centimeters, etc. in any other unit, but when we start substituting in a numerical, okay, so we wish to convert it in meters so that you will not commit any mistake in the consistency of the units. This MS, mass of the sleeve, the mass of the sleeve, this entire sleeve, I am considering only half of the sleeve here and half of the sleeve here. This is the entire sleeve, and this sleeve is of mass inverse. It is expressed in kg. And MB is the mass of each ball. I am taking one ball here, the other ball is this side, and MB is the mass of each ball, and that is also in kg. Alpha is the angle made by the upper arm with the axis of the spindle. So the extension of this angle is alpha. I have drawn a line parallel to the spindle, and therefore this angle also is alpha. Alpha is the angle made by the upper arm with the spindle axis. Similarly, beta is the angle made by the lower arm with the spindle axis. This line is parallel to that, and therefore this angle is beta. And H, a very important term. This is the distance between this point. So what is this point? This point is the intersection of the upper arm with the spindle axis. This is the spindle axis, this is the upper arm, the extension of the upper arm, this is the point which is the intersection of the intersection of the upper arm with the spindle axis. This point and this. And what is this? This is the plane of rotation of the balls. The distance of the intersection of the upper arm with the spindle axis from the plane of rotation of the balls is known as height of the governor. This is very important term, and this we call it as height of the governor. Okay, knowing and being familiar with all these terms, now probably I can go for what is called as analysis. Okay, so when I mean analysis, so I am going to relate all these terms, and when we take up a numerical, some of these things are unknown and and that is what we are going to find it out. So now, before I proceed, what I do is I make a small construction here. I extend the upper arm and just extend here, draw it. And similarly, I extend the sleeve, extend here. The intersection of the sleeve and the upper arm is what is called as, I denote it by a letter I. I is very familiar. Probably in kinematics of machines, we used to call it as instantaneous center. So I is known as instantaneous center of the lower arm. Okay. So probably why it is called, etc. I don't want to go into that. I shall proceed further. I would like to continue. Okay. So now one more small things. This line is this angle is alpha. This line is parallel. This is line is parallel, and this is the extension. Therefore, this angle is also alpha. On the same lines, this line and this line they are parallel, and this is beta and this is beta. And before I can start writing applying the equilibrium condition, one small last thing. So I know that the weight of the sleeve, the mass of the sleeve is ms, the weight of the sleeve is ms multiplied by g. That will be acting, imagined at the center of the sleeve. This ms into g, I can say that I can resolve it into, say, half part is coming here, and then another half part is coming this side. So I am not considering the other half, therefore I shall be considering only this half. Therefore, the weight of the sleeve, what I have to consider is only ms into g by 2. Okay, this is one force. Then each ball is having mass mb, therefore it is having weight and it acts vertically downwards, and therefore mb into g is the vertically downward force which is acting at point B. So this mass, this point mass which is revolving at a distance r, it is rotating at omega, therefore it is having a centrifugal force what is equal to Fc, which is equal to mb into omega square r. So these are the only three forces that are acting on it, and this ball is in a equilibrium state. So now so I know the equilibrium conditions. One of the equilibrium conditions is the sum of the moments due to all the forces is 0, and that is what I would like to apply. So I would like to apply sigma m about point I is equal to 0. This is what I would like to write down. And I write down the corresponding moments, etc. And that's what I say that it is analysis. Okay. So now Fc, the moment due to Fc about point I. Okay. So that is equal to Fc multiplied by the perpendicular distance, that is BD, and that is forming in a clockwise moment. This is forming clockwise moment. Then the moment due to this force ms into g upon 2 multiplied by Ci, this is the anti-clockwise moment. Then mb into g multiplied by di is what is called as the anti-clockwise moment. So there are two anti-clockwise moments and one clockwise moment, and they have to be balanced. That's what I am going to write down. And therefore, first let me write down the anti-clockwise moments. ms into g divided by 2 multiplied by Ci plus mb into g multiplied by di is equal to mb into omega square into r multiplied by bd. Okay, this is the moment equation. Okay, I simplify it. I wish to simplify further. Okay, probably I can write it ms into g upon 2. Okay, this BD term I would like to take it to the left hand side. I would like to take it to the left hand side. I can say that it is Ci, and at the same time, and Ci, I would like to rewrite it as CD plus Di. CD plus Di divided by BD. This term. This BD I am taking it to the left hand side. Similarly, plus mb into g into di divided by bd. This is equal to whatever bd is removed, and therefore it is mb into omega square into r. Okay, so for the simplification, we can verify it now. CD upon BD. CD upon BD. CD is this CD divided by BD. So this angle is beta. So therefore, CD upon BD is nothing but tan beta. So therefore, I can simplify this as MS into G divided by 2 into. So this term I am separating it. CD upon BD plus DI upon BD. Okay, CD upon BD is nothing but tan beta plus DI upon BD, DI upon BD, this angle is alpha, therefore this is tan alpha, tan beta plus tan alpha. So plus MB into G. So DI divided by BD, DI divided by BD is tan alpha, tan alpha. This is equal to MB into omega square into R. Okay, so now MS into G divided by 2. Okay, what is tan beta? Okay, tan beta and tan alpha. Okay, before that, I would like to take tan alpha outside here. Tan alpha. So if I do that, it is tan beta divided by tan alpha. From this term, plus 1. Plus, okay, so MB into G into tan alpha is equal to MB into omega square into R. Okay, from this term, so here also tan alpha both common, therefore I shall take tan alpha outside. So this is going to be MS into G divided by 2 into bracket. This I write it as 1 plus tan beta divided by tan alpha, I shall write it as K. 1 plus K plus MB into G, the whole thing. This is equal to MB into omega square into R. Okay, tan alpha, go back here. So I would like to make use of this triangle. Make use of this triangle. This angle also is alpha. Alpha is opposite side. This is R divided by this value. This is nothing but H. So tan alpha is equal to R divided by H into bracket. Okay. So probably I should just reshuffle this term. MB into G. This term I am writing it first. Plus MS into G divided by 2 into 1 plus K, the whole thing. Okay, and this is equal to MB into omega square into R. Okay, I can cancel this R and R. Okay, keeping omega square here and the rest all things, this MB also I send it to this side and therefore write an expression for what is called as omega square is equal to and this G also I can take it outside here. So G divided by H. Omega square is equal to G divided by H into bracket MB plus MS into 1 plus K divided by 2 into bracket MB. Okay, this is the expression for the speed of the governor, and whatever this speed we call it as equilibrium speed, because the governor balls are revolving at a constant speed. It is in equilibrium position. The sleeve is not moving upwards or not moving downwards, and it is in equilibrium position, and therefore this speed is called as equilibrium speed. Okay, now omega square I have. If you want to get omega, then whatever you simplify this and take the square root, you get omega, that is the radians per second. Of course, MB, MS are in kgs, and G is meter per second square. H is the height of the governor. This is also in meters. Then if you are not happy or the problem requires the speed in RPM, from this omega you have to find out, convert it into what is the speed in RPM. and that speed is called as equilibrium speed. Okay, I hope you have understood. If you have any doubt, you can ask me any question and then I will be able to answer. Thank you.